Somewhere out in the galaxy, a dead star is sitting on the edge of a cliff. It holds more mass than our sun, yet it is squeezed into a ball no wider than a city. For now, something deep inside it is pushing back against its own crushing gravity, holding the line. But that defense has a breaking point. Add just a little more mass or let it spin a little slower, and in a few thousandths of a second, the entire object loses. Nothing in known physics can stop what happens next. The star vanishes behind a horizon of its own making and becomes a black hole, hiding everything it once was. So, what is the invisible thing holding it up tonight, and what finally makes it fail? Before we go any further, if you find this kind of deep dive into the universe fascinating, taking a second to like or subscribe really does help this channel keep going. It's a small thing for you, but it means a lot to me. Now, let's begin. Picture a single teaspoon. An ordinary teaspoon, the kind you stir into a cup of coffee without a second thought. Now imagine dipping that teaspoon into the object we're going to explore tonight and scooping out the smallest possible amount of its material. That teaspoon would weigh roughly 4 billion tons. Not 4 tons, not 4,000, 4 billion. That is more than the combined weight of every car, every truck, every ship, and every building in a large city, all balanced on a single spoon. And that is just a teaspoon. The whole object holds more material than our entire sun, yet it is squeezed into a ball so small you could drive across it in the time it takes to finish a sandwich. We're talking about something around 20 kilometers wide. A neutron star. More mass than a star, packed into the footprint of a city. Now hold that image in your mind, because here is the thing that should genuinely disturb you. An object that dense should not be able to exist at all. By every rule of everyday physics, it should crush itself out of existence in an instant. The gravity at the surface of a neutron star is so ferociously strong that if you could somehow stand on it, you would be flattened into a smear thinner than a sheet of paper before you even understood what was happening. The pull is something like 100 billion times stronger than the gravity you feel on Earth right now. A pebble dropped from just 1 meter up would hit the surface at well over 1,000 kilometers per second. Gravity this powerful wants one thing and one thing only. It wants to pull every scrap of that matter inward toward the center and keep pulling until there is nothing left to pull on. It wants to collapse the whole thing into a single point. And yet, for now, it doesn't. The neutron star sits there, stable, holding its shape, defying the very force that is trying to annihilate it. Something inside is pushing back. Something is winning a standoff against the most relentless force in the cosmos. So, the first question, the question everything else depends on, is simple to ask and strange to answer. What on earth is holding this thing up? To understand the answer, we first have to understand what this matter even is, because it is nothing like the matter you are made of. Take an ordinary object, a rock, a chair, your own hand. Why doesn't your hand collapse under its own weight? Why can you press your palm against a table without the two of them merging into one solid lump? The answer is that ordinary matter is almost entirely empty space. An atom is mostly nothing. If you blew up a single atom to the size of a sports stadium, the nucleus at its center would be about the size of a marble sitting on the 50-yard line, and the electrons would be tiny specks whirling around the very outer rows of the stands. Everything in between is empty. The reason solid objects feel solid, the reason your hand doesn't sink through the table, is that the electrons in your hand and the electrons in the table refuse to overlap. They repel each other. That electromagnetic standoff between electrons is what gives ordinary matter its strength, its stiffness, its ability to hold a shape against gravity. But here is the problem. That kind of resistance is weak. It works fine for chairs and mountains and planets. It even works for ordinary stars, where the outward push of heat and radiation from nuclear fusion holds the star up against its own gravity. But when a massive star reaches the end of its life and its core can no longer fuse elements to produce that outward push, gravity finally gets its way. The core collapses. And when it does, the pressure becomes so unimaginable that the empty space inside atoms simply gets crushed out of existence. The electrons, which normally keep their distance, get rammed straight into the protons sitting in the nuclei. When an electron and a proton are forced together hard enough, they merge and become a neutron, releasing a ghostly particle called a neutrino in the process. This happens not to one atom, not to a billion atoms, but to very nearly every atom in the collapsing core, all at once, in a fraction of a second. The result is something almost beyond imagining. All the empty space, gone. The matter that used to be a sprawling cloud of atoms with vast gaps between the nuclei has been compressed into a substance where the particles are packed shoulder to shoulder, nearly touching, with no gaps left at all. It is essentially one gigantic atomic nucleus, the size of a city. A sea of neutrons crushed together at a density you cannot find anywhere else in the known universe outside of this kind of object. This is what a neutron star is made of, and this is the matter that, somehow, holds the line against gravity. So we return to our question. If the empty space is gone, if the electrons have been crushed into the protons, what is left to push back? What stops the collapse from simply continuing all the way down? The first part of the answer comes from one of the strangest and most beautiful rules in all of physics. It is a quantum rule, and it goes by the name of the exclusion principle. To understand it, you don't need any mathematics. You just need to understand one bizarre fact about a certain family of particles. Neutrons, along with protons and electrons, belong to a category of particle that physicists call fermions. And fermions have a rule: they will never, ever break. No two identical fermions can occupy the exact same quantum state at the same time. In plain language, two of them are forbidden from being in the same place, doing the same thing with the same energy. They are antisocial in the most fundamental way the universe allows. Each one demands its own unique state, its own seat, and absolutely refuses to share it with another. Here's an analogy that gets close to the truth. Imagine a vast concert hall, and imagine that the seats are arranged in tiers, with the cheap, low-energy seats down at the bottom, and the expensive, high-energy seats climbing up toward the ceiling. Now imagine you have to seat a crowd of fermions, and the rule is absolute. One fermion per seat. No exceptions, no sharing, no sitting in laps. Naturally, the first fermions fill up the cheap seats at the bottom, because everything in nature prefers the lowest energy it can get. But once those bottom seats are full, the next fermion has no choice. It cannot squeeze into an occupied seat because the rule forbids it. So it is forced to climb higher, into a more expensive, higher energy seat. The next one is forced higher still. As you keep packing fermions in, they are driven up and up into higher and higher energy states, not because they want to be there, but because every lower state is already taken and the rule simply will not bend. Now, think about what that means for a neutron star. You have crammed an almost incomprehensible number of neutrons into a tiny volume. The low energy states fill up almost instantly, and the neutrons are forced into higher and higher energy states, which means they are forced to move faster and faster. Even at low temperature, even if you could cool this matter down toward absolute zero, those neutrons would still be zipping around at enormous speeds, because the exclusion principle leaves them no other option. And fast-moving particles flying around at tremendous speeds, exert pressure. They push outward. They resist being squeezed any tighter, because squeezing them tighter would force them into even higher energy states, and they fight that with everything they have. This outward push is called neutron degeneracy pressure, and it is the first line of defense holding the star up. What makes it so remarkable, so utterly unlike anything in your daily experience, is that it has nothing to do with heat. The pressure in a normal gas, the pressure in the air in your room, comes from temperature. Heat the air up and it pushes harder. Cool it down and it pushes less. But degeneracy pressure doesn't care about temperature at all. It is a pure consequence of the quantum rule. You could cool a neutron star down to almost nothing, and this pressure would still be there. Still pushing, still standing firm. It is a kind of stubbornness woven into the deepest fabric of matter itself. The neutrons resist collapse not because they are hot, but because they are forbidden by the laws of the universe from getting any closer together without paying an enormous energy price. If this sounds familiar, there is a reason. The very same kind of pressure, except provided by electrons rather than neutrons, is what holds up a different kind of stellar corpse called a white dwarf. A white dwarf is what a star like our Sun will eventually become. A dense ember about the size of the Earth held up by electron degeneracy pressure. But a white dwarf has a limit. Pile too much mass onto it, and the electrons can no longer hold the line. And the whole thing collapses further, which is precisely what crushes the electrons into the protons, and creates the sea of neutrons we have been describing. So a neutron star is, in a sense, the next rung down on a ladder of collapse, held up by a tougher, denser version of the same quantum stubbornness. And here, just when you think you have the answer, the story takes a turn that fooled the very first scientists who studied it. Because it turns out that neutron degeneracy pressure all by itself is not actually strong enough. When physicists first worked out the mathematics of neutron stars back in the 1930s, they calculated how much mass degeneracy pressure alone could support. And the number they got was surprisingly small. If neutrons did nothing but obey the exclusion principle, a neutron star could hold no more than around 3/4 of the mass of our Sun before gravity overwhelmed it and crushed it. That should have been the end of the story. But it wasn't, because nature kept showing us neutron stars far heavier than that. We have now measured neutron stars that weigh 2 times the mass of the Sun and more. The matter is holding up a load more than twice as heavy as the simple calculation said was possible. Something else, something powerful, must be pitching in to help. Degeneracy pressure is real and it matters, but it is not the whole answer. It is not even the biggest part of the answer. So, what is the missing ingredient? To find it, we have to look at the neutrons themselves, not as abstract particles obeying a quantum rule, but as physical objects with real structure and real forces between them. And this brings us to the strongest force in all of nature. A force so powerful it is literally named the strong nuclear force. The strong force is the glue that holds the nucleus of every atom together. Inside a nucleus, you have protons packed close, and protons all carry positive electric charge, which means they should violently repel one another and fly apart. The only reason any nucleus holds together at all is that the strong force, acting over tiny distances, overpowers that electric repulsion and binds the particles together. It is, by an enormous margin, the most powerful of the fundamental forces. But the strong force has a peculiar personality, and that peculiarity is the key to everything. At very short ranges, the strong force is attractive. It pulls the particles in the nucleus together and binds them, but push two of these particles closer and closer, force them right up against each other and try to shove them even nearer, and the strong force suddenly flips its character. At extremely short distances, it stops pulling and starts pushing back, and it pushes back ferociously. It becomes intensely repulsive. It is a bit like a powerful magnet that snaps two objects together, but then refuses to let them actually merge, slamming on the brakes the instant they get too close. The particles have what physicists sometimes call a hard core, a region of fierce resistance that simply will not let them be compressed past a certain point. Inside a neutron star, the neutrons are packed so tightly that they are jammed right up against this hard core of resistance. They are practically touching, sitting at the exact distance where the strong force has turned from a gentle pull into a brutal shove. And so, when gravity tries to crush them even closer together, it runs headlong into that fierce, hard core of resistance, standing in its way, refusing to yield. This strong force repulsion provides most of the muscle in the standoff. It is the heavy weight that lets a neutron star carry 2 suns worth of mass, when degeneracy pressure alone could only carry a fraction of that. So now we can finally see the standoff for what it really is. It is a competition. On one side, gravity, trying to pull everything inward, relentless and patient, growing stronger the more it succeeds. On the other side, 2 defenders working together. There is the quantum stubbornness of degeneracy pressure, the neutrons forbidden from sharing states and forced into furious motion. And there is the raw power of the strong nuclear force, the hard core of resistance that refuses to let the particles be crushed any nearer. For a stable neutron star, these defenders win. They push outward exactly as hard as gravity pulls inward, and the object settles into a tense, perfect balance, frozen on a knife's edge between holding together and falling apart. That balance is what we see when we look at a neutron star, not peace exactly. More like a wrestling match where both sides are straining with everything they have, and, for the moment, neither one can move the other. But notice something unsettling about that picture. Both of these defenses have limits. Degeneracy pressure can only push so hard. The strong force can only resist so much. They are mighty, but they are not infinite. And gravity, crucially, is patient. Gravity never tires, never weakens, never gives up. So there is a question hanging over this entire standoff, a question we will return to. What happens if you tip the balance just slightly in gravity's favor? How much can these defenders take before they break? Before we get there though, we have to confront something genuinely humbling. Because for all the confidence with which I have just described what holds a neutron star up, the truth is that physicists do not fully know what the matter inside one actually is. And the deeper you go, the less anyone knows. The outer layers of a neutron star are reasonably well understood. There's a thin atmosphere, then a solid crust made of crushed nuclei arranged in a rigid crystal lattice, a crust thought to be billions of times stronger than steel. Below that, the neutrons begin to flow freely, behaving like a frictionless liquid, a superfluid that can swirl and circulate without resistance. So far, so strange, but still within reach of our theories. The real mystery lies further down, in the very core, where the density climbs to values we cannot reproduce anywhere on Earth, and cannot create even in our most powerful particle accelerators. We simply have no way to make matter this dense and study it directly. We can only build theories and squint at distant stars, trying to read the answer in their behavior. And the theories disagree, sometimes wildly. In the deepest core, where the crushing reaches its absolute peak, the matter might still be a sea of neutrons, packed and resisting as we described. But it might be something far stranger. Some physicists suspect that at these densities the neutrons begin to transform, and heavier, more exotic cousins of the neutron, particles called hyperons, start to appear in the mix. Others propose that the matter might host strange new states, condensates of particles behaving in ways that have no equivalent in ordinary experience. And then there is the most dramatic possibility of all. The matter might stop being made of neutrons entirely. Remember that neutrons are not truly fundamental. Each neutron is itself made of smaller particles called quarks, 3 of them bound together so tightly that under normal conditions they can never be pulled apart and never exist on their own. They are permanently imprisoned inside the neutron. But push the density high enough, squeeze the neutrons hard enough, and some theories suggest the walls of that prison could finally break down. The neutrons would dissolve, their boundaries melting away, and the quarks would spill out and mingle freely in a kind of soup that has never been seen, a substance sometimes called quark matter. There is even a wilder version of this idea, a hypothetical form called strange matter, which, if it exists, might be the most stable form of matter in the universe, and might fill the hearts of these stars in ways we can barely guess at. We do not know if any of this is true. We only know that we cannot rule it out. Why does this uncertainty matter so much? Why isn't it just an interesting footnote for specialists? Because the answer determines exactly how stubborn this matter is. Physicists have a name for that stubbornness. They call it the equation of state. And you can think of it as the answer to a single question. When you squeeze this matter, how hard does it push back? Matter that pushes back hard is called stiff. Matter that gives way more easily is called soft. And whether the matter inside the neutron star is stiff or soft depends entirely on what that matter actually is. On whether the core is full of neutrons or hyperons or free quarks or something stranger still. Stiff matter can hold up more mass before gravity wins. Soft matter breaks sooner. So the unknown identity of the core is not a small gap in our knowledge. It is the crack running straight through the foundation of this entire story. Until we know what the matter is, we cannot say precisely how much weight the standoff can bear, and therefore, we cannot say precisely when it will fail. This is one of the great unsolved problems in physics today, and it is genuinely strange to sit with. We can build a bridge and know exactly how much load it will carry before it buckles, because we understand steel and concrete down to the atom. But here is an object more massive than the sun, sitting out in space, and we cannot tell you for certain what it is made of in its heart, or exactly how much it can hold. The matter at the center of a neutron star may be the most extreme substance in the cosmos, and it is hidden from us behind a wall of density we have no way to climb. What we can say with complete confidence is this: the standoff is real, the defenders are mighty, and the balance is exquisitely fine. A neutron star is not a quiet, settled thing. It is a battle, frozen in the middle of its most violent moment. Gravity straining inward, degeneracy pressure, and the strong force straining outward. The whole structure held together by forces operating at the very edge of what nature permits. And the defenders, for all their power, are finite. There is a load they cannot carry. There is a line somewhere out there that, if the star ever crosses it, ends the standoff forever. So that is the situation as it stands tonight. Out in the galaxy, a dead star holds more mass than our sun inside a sphere the size of a city, and something deep inside it is pushing back against gravity hard enough to keep it from vanishing. We now know what that something is: the quantum refusal of neutrons to share their states, and the iron resistance of the strongest force in nature, working together against a foe that never rests. But we also know the defenders have a breaking point, and we know there is a mystery buried in the core that keeps us from saying exactly where that breaking point lies. The question that follows is the one that should make the hair on your arms stand up. If there is a line the star cannot cross, where is it? What sets it? And what could ever push a stable, balanced neutron star close enough to that edge for the whole thing to finally, catastrophically lose? Let me ask you to imagine a weightlifter. Not just any weightlifter, but the strongest one who has ever lived, standing beneath a bar loaded with more weight than seems physically possible. His arms are locked, his whole body is straining, and the bar is holding steady above his head. He's not lifting it higher. He's not letting it drop. He's simply holding the line, every muscle in his body fighting to keep that bar from crushing him. Now imagine that someone walks over very calmly and adds one more small plate to the end of the bar. Just a little extra. And in that instant, everything fails. The arms buckle, the bar comes down, and there is no halfway. No slow sag, no second chance. One moment he's holding, and the next, he is not. A neutron star lives exactly like that weightlifter. We established that it survives by a standoff, with gravity pulling inward and the combined force of quantum pressure and the strong nuclear force pushing outward, locked in perfect balance. But a standoff like that can only hold so much. There is a maximum load. There is a heaviest bar that the strongest defenders in the universe can possibly keep aloft. And the most important fact about that maximum is also the most unsettling. Once you cross it, there is no gentle warning. There is no slow decline. The defenders either win or they lose. And when they lose completely and almost instantly. So the question that drives everything tonight becomes sharp and specific. How heavy is too heavy? Where exactly is the line? This is where we meet one of the most important numbers in this entire story. A number that comes with 3 names attached to it. The scientists who first worked it out: Tolman, Oppenheimer, and Volkoff. Back in the 1930s, these physicists took the equations that describe how matter resists gravity and pushed them to the breaking point, asking the simplest possible version of the question. How much mass can a ball of this incredibly dense material hold before its own gravity wins? The answer they arrived at is now called the Tolman-Oppenheimer-Volkoff limit, or more commonly, just the TOV limit. It is the maximum possible mass of a neutron star. Pile on more than this, and no known pressure in the universe can stop the collapse. The line gets crossed, the star loses, and a black hole is born. Now here is where I have to be very careful and very honest with you, because this is the kind of number that people love to pin down to a single, tidy figure, and the truth refuses to cooperate. You will sometimes hear that the maximum mass of a neutron star is about 2 1/6 times the mass of our Sun, or perhaps 2 1/3, or 2.5. And the honest answer is that nobody knows the exact value. What scientists can tell you is a range. The TOV limit sits somewhere between roughly 2 times the mass of the Sun and 2.5 times the mass of the Sun, and the best current evidence clusters near the lower portion of that range, somewhere around 2.25 solar masses, give or take. But that is a window, not a pinpoint. And the reason it is a window, the reason we cannot simply state one definitive number and be done with it, leads us straight back to the great mystery we ended on earlier, the unknown matter in the core. Remember the equation of state, the answer to the question of how hard this matter pushes back when you squeeze it. Stiff matter, the kind that resists fiercely, can hold up more mass before failing, which pushes the TOV limit higher toward the upper end of that range. Soft matter, the kind that gives way more easily, breaks sooner, which drags the limit lower, and whether the matter in the deepest core is stiff or soft depends on what it actually is, on whether it is a sea of neutrons or a stranger soup of hyperons or free quarks. So the uncertainty in the maximum mass is not laziness on the part of scientists. It is a direct reflection of a genuine gap in our knowledge of physics. The exact location of the line is hidden inside the same wall of density that hides the nature of the matter itself. We know the line exists. We can fence it into a range. We cannot yet stand on it and read off a single number. And anyone who tells you the maximum mass of a neutron star with perfect confidence to several decimal places is telling you something the universe has not yet told us. For a long time, the story could have ended right there, with a single fixed line and the simple rule that crossing it means collapse. But nature, as it so often does, turns out to be far more interesting than that. Because here is a fact that changes everything. The line is not in the same place for every star. The maximum mass a neutron star can hold is not one fixed value carved into the cosmos. It can move, and there are two things that can move it. Two tricks that let a neutron star temporarily hold far more mass than it has any right to. The first is spin. The second is heat. Together, they turn what looked like a single hard wall into something more like a sliding scale. And understanding them is the key to understanding why some doomed stars get to cheat death. At least for a while. Let us start with spin, because it is the more powerful of the two and the more beautiful. To feel how it works, you do not need a neutron star. You just need a memory of a childhood playground. Think of a merry-go-round, the spinning kind you push and then leap onto. When it is still, you can sit comfortably near the edge, but get it spinning fast, really fast, and you feel a force trying to fling you off, pulling you outward, away from the center. You have to grip hard to keep from being thrown. That outward effect, the tendency of a spinning object to throw its own material away from the axis, is the heart of the trick. Now picture a neutron star spinning. And neutron stars do not spin gently. Some of them rotate hundreds of times every single second. There are neutron stars out there turning so fast that a point on their surface is moving at a sizable fraction of the speed of light. A spin so absurd that the entire city-sized object completes a full rotation in the time it takes you to say a single word, and then does it again, hundreds of times over, in one breath. When an object spins that fast, its own rotation tries to fling its material outward, away from the center, in exactly the way the merry-go-round tries to fling you off. and the outward tendency works directly against gravity. It is as if the star has hired an extra defender, a centrifugal scaffolding that holds the outer material up and shares the burden that gravity is trying to impose. Gravity is still pulling inward as hard as ever, but now it is not facing only degeneracy pressure and the strong force. It is also fighting the star's own furious rotation, which is propping up the structure from the outside. The faster the star spins, the more help this scaffolding provides, and the more mass the star can hold before the standoff breaks. This is a genuinely strange and important idea, so let me state it as plainly as I can. A rapidly spinning neutron star can support more mass than a slowly spinning one made of the exact same material. The spin literally raises the line. It pushes the breaking point higher, lets the star carry a heavier load than the TOV limit would otherwise allow. The increase can be substantial, raising the maximum mass by something like 20% above what a non-spinning star could hold. So a star spinning at a tremendous rate might cling to existence carrying a mass that would have crushed a still version of itself in an instant. The rotation buys it room. The rotation, for a time, holds back the inevitable. But notice the catch hiding in that idea, because it is everything. Spin can be lost. A weightlifter who is bracing against a bar with a clever trick of leverage is fine right up until the moment he loses that leverage. And a neutron star spinning at the edge of what its rotation can support is in exactly that position. As long as it keeps spinning fast, it holds. But neutron stars do not spin fast forever. They gradually slow down over time, bleeding away their rotational energy, mostly by dragging their immense magnetic fields through the surrounding space, which acts like a brake. The spin winds down, the centrifugal scaffolding weakens, and the extra support it was providing fades away. We will return to the consequences of that in a moment, because they are profound. For now, hold onto the central point. Spin raises the line, but spin is temporary, and a star leaning on its own rotation to survive is leaning on something it is slowly losing. The second trick is heat, and it works in a different way, but toward the same end. Now I have to be careful here, because earlier I made a point of telling you that degeneracy pressure does not care about temperature, that the quantum stubbornness of the neutrons holds the star up whether it is hot or cold. That is true, but heat can still contribute its own additional push, layered on top of the degeneracy pressure, and in certain dramatic circumstances, that extra push becomes important. Think of it this way. In an ordinary gas, heat means the particles are moving faster, slamming into things harder, pushing outward more forcefully. A hot gas exerts more pressure than a cold one. Inside a normal, settled neutron star, this thermal pressure is a tiny contribution, drowned out entirely by the degeneracy pressure and the strong force. The star is essentially cold as far as its structure is concerned, even though its surface might glow at 1,000,000 degrees, because the pressures holding it up are so overwhelmingly larger than anything heat could add. But there are moments in a neutron star's life when it is not cold, when it is, in fact, blisteringly, violently hot in a way that genuinely matters to its structure. And in those moments, the thermal pressure stops being a rounding error and starts being a real defender, adding its own outward push to the standoff and, like spin, temporarily raising the line. A ferociously hot neutron star can support more mass than a cold one, because the heat itself is pushing back against gravity. The catch, of course, is the same catch as before, only faster. Heat fades. A hot object radiates its energy away into space and cools, and a neutron star, for all its extremity, is no exception. The thermal support is the most fleeting of all. It is the defender most certain to abandon its post. Now, when do these tricks actually come into play? When is a neutron star spinning at the absolute edge of what rotation can support, or glowing hot enough for thermal pressure to matter? The answer is that these are not the conditions of a quiet, settled, ancient neutron star. These are the conditions of birth and violence. And this brings us to a distinction that is going to matter enormously for everything that follows. Because once you accept that the line can move, you realize that not all neutron stars are sitting in the same place relative to it. Some are comfortably below the line, some are above where the line would be if they were cold and still, surviving only because spin and heat have temporarily raised it. And these are genuinely different kinds of objects, living genuinely different lives, headed toward genuinely different fates. Physicists divide them into 3 categories, and learning to tell them apart is the key that unlocks the rest of this story. The first category is the ordinary neutron star. This is the kind we have mostly been picturing, the kind that makes up the vast majority of the neutron stars in our galaxy. An ordinary neutron star has a mass safely below the TOV limit. It is held up by degeneracy pressure and the strong force alone, with no need for any tricks. It does not require spin to survive, and it does not require heat. It could be turning slowly, it could be cold, having radiated away its birth heat over millions of years, and it would still hold together just fine because its mass is simply below what its internal forces can support without any extra help. An ordinary neutron star is stable in the deepest sense. It is not leaning on anything that can be taken away. Left undisturbed, it can sit out in space essentially forever. A quiet, dense ember, holding its shape for billions upon billions of years. This is the crucial point to hold on to. An ordinary neutron star, all on its own, is not doomed to collapse. It is not waiting to become a black hole. It is stable, and unless something acts upon it from outside, it will simply remain a neutron star for the rest of cosmic time. We will come back to this because it cuts against a common and mistaken assumption that every neutron star is just a black hole in waiting. The second category is far more precarious, and it is called the supramassive neutron star. A supramassive neutron star is one whose mass is too great to be held up by degeneracy pressure and the strong force alone. If it were sitting still, it would already have collapsed. It is over the cold, non-spinning limit. The only reason it survives is rotation. It is spinning fast enough that the centrifugal scaffolding we described is propping it up, holding the extra mass that its internal forces cannot. A supermassive neutron star is, in the most literal sense, surviving on borrowed time, and the loan is its spin. It is the weightlifter holding the impossible bar through sheer clever leverage, fine for as long as the leverage lasts. And we already know what happens to spin. It winds down, the star slows over time, the rotational support weakens, and there comes a moment when the spin is no longer fast enough to hold the mass aloft. At that moment, with no trick left to save it, the star crosses the line and collapses. A supermassive neutron star is not stable in the way an ordinary one is. It is a temporary state, a configuration that exists only as long as the spin holds out, destined to collapse the moment its rotation falls below the critical threshold. It might survive for seconds, or minutes, or far longer, depending on how fast it is spinning and how quickly it slows. But its fate, eventually, is sealed. The third category is the most extreme and the most short-lived of all, and it is called the hypermassive neutron star. A hypermassive neutron star carries even more mass than a supramassive one, so much mass that uniform spin alone cannot hold it up. It survives only by combining every trick at once and adding one more. It uses heat, blistering thermal pressure from a violent birth. It uses spin, but crucially it uses a special kind of spin called differential rotation, which means that different parts of the star are rotating at different speeds, the inner regions whirling at one rate, while the outer regions whirl at another. This differential rotation provides a tremendous amount of extra support, far more than uniform spinning could, because it lets the star's rotation work even harder to prop up its structure. A hypermassive neutron star is the weightlifter holding a bar so heavy that he needs every muscle, every trick of leverage, and a surge of adrenaline all at the same time. And even then, he can only hold it for the briefest instant before something gives. These objects are propped up by the most fragile and fleeting of supports. The heat radiates away. The differential rotation smooths out because the friction-like forces inside the star tend to drag the different layers toward spinning at the same rate, erasing exactly the difference that was holding everything up. And when those supports vanish, as they vanish almost immediately the collapse comes. A hypermassive neutron star might survive for mere milliseconds, 1,000th of a second, a blink within a blink. It is less a stable object than a momentary configuration of matter caught in the act of failing. Do you see how the picture has transformed? We began with the image of a single fixed line, a wall that, once crossed, meant certain collapse. And that picture is not wrong, exactly, but it was far too simple. The real picture is a sliding scale, a line whose position depends on how fast the star is spinning and how hot it is, with three distinct kinds of objects arranged in relation to it. The ordinary neutron star, sitting comfortably below the cold line, stable and in no danger. The supermassive neutron star, held above the cold line by spin alone, surviving on borrowed time as its rotation winds down. And the hypermassive neutron star, held above even the spinning line by the desperate combination of heat and differential rotation, surviving only for the briefest flicker before its supports fail. And here is the thread that ties all three together. The thread that turns this from a catalogue into a story. Every one of these supports, except for the basic degeneracy pressure and strong force that hold up an ordinary star, is temporary. Spin can be lost. Heat fades. Differential rotation smooths out. All of these are loans, not gifts, and every loan eventually comes due. So a supermassive or hypermassive neutron star is not a thing that exists. It is a thing that is in the process of failing, captured in a moment of borrowed survival with the clock already running down. The only question is how long the borrowed time lasts, and that is a question that ranges across an astonishing span of scales. Milliseconds for the hypermassive, seconds or minutes for some supramassive stars, and in certain cases we will encounter, potentially far longer, a slow fuse burning quietly toward an end that may not come for a very long time. This raises a question that should be nagging at you by now. We have these three categories, these three relationships to the line. But how does a neutron star end up in one category rather than another? How does a star come to carry more mass than it can hold on its own, to find itself supramassive or hypermassive, leaning on spin and heat, just to survive the moment? An ordinary neutron star, after all, is born below the line and stays there. Something has to push a star past the cold limit, has to load that extra weight onto the bar, has to put it in the precarious position of needing tricks to survive at all. Stars do not simply decide to become unstable. Something acts upon them. And notice too, that we now understand why the timing of collapse is such a strange and variable thing. If the support is heat and differential rotation, the loan is tiny and the collapse comes in milliseconds. If the support is steady, spin alone, the loan can last far longer, the star slowly winding down over seconds or minutes or more before it finally crosses the line. The nature of the support determines the length of the reprieve. A merger remnant glowing hot and whirling unevenly is living on the shortest of fuses. A coldly spinning supermassive star is on a much longer one. Same ultimate fate, wildly different clocks, all set by which temporary defender happens to be holding the line. So we have arrived at a precise and sharpened understanding. There is a maximum mass for a neutron star, the TOV limit. We know it lies somewhere in a range rather than at a single certain value, because the matter in the core is still a mystery. We know that spin and heat can temporarily raise that limit, letting a star hold more than it otherwise could. We know that this gives us three kinds of objects: ordinary, supermassive, and hypermassive, arranged from stable to fleeting. And we know that the temporary supports, the spin and the heat, and the differential rotation are loans that must eventually be repaid, which means that a star surviving on them is a star living on borrowed time. What we do not yet know is how a star gets loaded onto that bar in the first place. What pushes a stable, balanced neutron star toward the edge? What siphons extra mass onto it, or slams it together with another star, or strips away the very spin that was keeping it alive? There are, it turns out, several different roads that lead a neutron star to the cliff's edge. Several distinct ways the universe conspires to load that final, fatal plate onto the bar, and each one tells its own story, with its own timescale and its own kind of violence. Those roads are where we turn next. There is a moment in old films where a character is balanced at the very edge of a rooftop, arms wheeling, and you know that the smallest thing, a gust of wind, a single misstep, will send them over. We've spent our time so far building exactly that moment for a neutron star. We know it survives by a standoff. We know there's a line it cannot cross. We know that spin and heat can shift that line, creating stars that live on borrowed time. But all of that describes a star teetering at the edge. It does not explain how it got there. It does not explain what finally tips it over. Because here is the thing. A neutron star does not simply decide to become unstable. An ordinary neutron star sitting alone in space is stable. It will not collapse. It will sit there, a quiet ember, for longer than the universe has so far existed. For it to cross the line and fall, something has to act upon it. Something has to load that final, fatal weight onto the bar, or steal away the support that was keeping the bar aloft. And it turns out there is not just one way the universe does this. There are several distinct roads that lead a neutron star to the cliff's edge, 4 of them in particular, and each one is its own kind of drama, with its own pace and its own character. Some take millions of years. Some take a fraction of a second. Let us walk each of them in turn, because to understand the collapse, you first have to understand how a star arrives at the place where collapse becomes inevitable. The first road is the slowest, the most patient, and in some ways the most quietly menacing. It is the road of accretion, of theft, To travel it, our neutron star cannot be alone. It must have a companion, another star orbiting close beside it, the two of them locked in a gravitational dance. This is not unusual. A great many stars in the galaxy come in pairs, born together and bound together for the whole of their lives. So picture a neutron star with an ordinary star as its partner, the two of them circling one another in the dark. The neutron star is enormously dense, which means its gravity, close up, is ferocious. And if the companion star drifts close enough, or swells up as it ages, that ferocious gravity begins to do something remarkable. It starts to pull the outer layers of gas right off the companion's surface. This stolen gas does not fall straight down onto the neutron star. The whole system is spinning, orbiting, so the gas spirals inward instead, swirling around the neutron star in a flattened, whirling disk, like water circling a drain. This is called an accretion disk, and it is a violent, blazing thing. The gas in it is moving at tremendous speeds, rubbing against itself, heating up to millions of degrees, glowing fiercely in X-rays as it spirals down and down. And eventually, layer by layer, that gas settles onto the surface of the neutron star itself. The neutron star is eating. It is slowly, steadily, over enormous spans of time, devouring its companion, and with every mouthful, it grows a little heavier. Now think about what that means in the light of everything we have learned. The neutron star may have started its life comfortably below the line, a perfectly stable, ordinary object, but it is gaining mass, drop by drop. Gram by gram, the scale is tipping. The bar is being loaded, not all at once, but with agonizing patience, over millions of years. And the defenders inside, the degeneracy pressure and the strong force, are being asked to hold more and more, creeping closer and closer to their absolute limit. For a long time, nothing seems to happen. The star eats, it grows, it holds, but the line is fixed, and the mass is rising toward it. And there comes a day, after all those slow millennia of theft, when the very last bit of gas settles onto the surface and tips the total over the edge. One final gram, no different from the billions of tons that came before it, and suddenly the defenders can hold no more. The standoff breaks. After millions of years of patient, almost imperceptible growth, the collapse comes in an instant. The slowest road of all ends in the fastest possible failure. There is something genuinely eerie about this road. The cause the collapse stretches back across geological time, across an unimaginably long process of slow feeding, and yet, the collapse itself, when it finally arrives, takes no longer than the others. The star spends an age creeping toward the cliff, and then falls off it in a heartbeat. And the trigger, the thing that actually does it, is utterly unremarkable. Just a little more gas, the same gas that had been arriving safely for ages, except that this particular helping happened to be the one that crossed the line. The second road is the opposite of the first in almost every way. Where accretion is slow, patient, and quiet, this road is sudden, catastrophic, and unimaginably violent. It is the road of the merger, the collision of two neutron stars. Picture not one neutron star with an ordinary companion, but two neutron stars orbiting each other. Two of these city-sized, sun-massed objects locked in a tight, fast orbit. As they whirl around one another, they stir the very fabric of space, sending out ripples called gravitational waves, and those ripples carry energy away from the system. As the energy drains, the two stars spiral closer together, orbiting faster and faster, drawing tighter and tighter over millions of years, until in the final moments, they are whipping around each other hundreds of times per second, and then they meet. When two neutron stars collide, it is one of the most extreme events the universe can produce. Two of the densest objects in existence, each more massive than the Sun, slamming together at a substantial fraction of the speed of light. In that instant, all of their combined mass is suddenly piled into a single object. And here is the crucial point. The combined mass of two neutron stars is very often more than the line allows. Two stars that were each individually stable, each comfortably below the limit, can produce a merged object that is far over it. The collision in a single stroke loads the bar with a weight no neutron star could ever hold while cold and still. So why doesn't the merged object collapse instantly? Why isn't a black hole formed the very moment the two stars touch? This is where everything we learned about spin and heat comes flooding back. Because the merger creates precisely the conditions that those tricks require. The collision is unbelievably violent and unbelievably hot, generating temperatures that make the resulting object glow with thermal pressure that genuinely matters. And the merger sets the resulting object spinning at a tremendous rate, often with exactly the kind of differential rotation we described. The inner and outer regions whirling at different speeds. In other words, the collision very often produces a hypermassive neutron star, that most extreme and fleeting of objects, surviving only by the desperate combination of heat and differential rotation, holding far more mass than it has any right to hold, for the briefest of moments. And we already know what happens to a hypermassive neutron star. Its supports are the most fragile of all. The heat begins to radiate away, the differential rotation begins to smooth out, the layers dragging each other toward a common spin, erasing the very difference that was holding the structure up. And so the merger remnant survives for perhaps a few milliseconds, 1,000th of a second or so, balanced on supports that are vanishing even as they hold before the collapse arrives. A blink within a blink, and the merged object that was a neutron star for the span of a few heartbeats of a housefly becomes a black hole. But not every merger plays out exactly this way, and the variations are part of what makes this road so rich. If the combined mass is only modestly over the line, the remnant might not be hypermassive but supramassive, held up by ordinary spin once the differential rotation has smoothed out. And that buys it more time, seconds rather than milliseconds. If the combined mass is enormous, far over the line, the remnant might not survive even a single millisecond, collapsing almost the instant the two stars touch, a process called prompt collapse, where the black hole forms essentially immediately. And in some cases, if the two stars were light enough, the merged object might actually settle into a single, larger, stable neutron star and not collapse at all, at least not right away. The road of the merger, in other words, splits into many paths depending on the masses involved, ranging from instant collapse to a reprieve of milliseconds to seconds to, sometimes, survival. But the common thread, for the heavier mergers, is the same. Two stable stars combine into one overweight remnant, and that remnant, propped up briefly by the violence of its own creation, eventually loses the standoff and falls. The third road is stranger and less obvious than the first two, and to understand it, we have to think back to where many neutron stars come from in the first place. A neutron star is typically born in the death of a massive star, in the catastrophic event called a core collapse supernova. The massive star runs out of fuel, its core collapses into a neutron star, and the outer layers of the star are blasted away in a titanic explosion. Now, I want to pause here and be very careful about something, because it is a point that is easy to confuse and important to keep straight. This original supernova, the explosion that creates the neutron star, is not the event we are discussing tonight. The collapse from neutron star to black hole is a separate thing, happening later by a different mechanism. The supernova makes the neutron star. The roads we are walking now are about what happens to that neutron star afterward. Do not let the two events blur together because they are genuinely distinct, separated sometimes by enormous stretches of time. With that clear, here is the third road, which is tied to that original explosion but happens in its aftermath. When the massive star explodes, blasting its outer layers outward, not all of that material necessarily escapes. The explosion hurls the star's outer shells into space, but the newborn neutron star sitting at the center has tremendous gravity, and some of that ejected material, instead of flying away forever, slows down, stops, and begins to fall back. This is called fallback. Material from the explosion that was thrown upward but did not reach escape velocity, raining back down onto the freshly born neutron star in the minutes and hours after the supernova. And this fallback material adds mass. A neutron star that was born just below the line, perfectly stable, might find itself buried under a rain of returning debris from its own creation, and that extra mass can push it over the edge. The collapse, in this case, follows fairly soon after the birth, a kind of delayed failure where the star survives the supernova, only to be undone by the very material the supernova threw up. It is as if the explosion that created the star also, in a sense, planted the seed of its destruction, sending up material that would come back down to finish the job. The fallback road is a reminder that a neutron star's most dangerous moments can come not from some distant external event millions of years later, but from the chaotic aftermath of its own violent birth, when the dust has not yet settled and the question of how much mass it will finally retain is not yet decided. And the amount of fallback can vary across an astonishing range, which is exactly what makes this road so much richer than it first appears. In some supernovae, only a thin trickle of material returns, a light dusting that nudges the neutron star a little heavier but leaves it comfortably stable. In others, the explosion is feeble, a weak and stuttering blast that barely manages to throw the outer layers clear at all. And when the explosion is that weak, an enormous quantity of the star's own body comes raining back down, far more than a trickle, a deluge of returning matter that buries the newborn neutron star within hours of its birth. In the most extreme version of this, the neutron star may exist as a neutron star for only the briefest interval before the avalanche of fallback overwhelms it entirely and drives it across the line. Astronomers have a striking name for the outward appearance of such an event. They call it a failed supernova. From the outside, you might expect a brilliant explosion, the death of a massive star lighting up its corner of the galaxy. Instead, there is a brief flicker, a faint flash, and then the star simply disappears. It does not blaze. It does not announce itself. It quietly disappears, because so much of its material fell back and collapsed that there was never a proper explosion to see in the first place. There are real candidates for this in the sky, massive stars that were being watched, and then, without the expected fireworks, were simply gone. A star that vanishes rather than explodes is one of the eeriest sights the cosmos can offer, and the fallback road is one of the ways it can happen. Now we come to the fourth road, and this one is perhaps the most haunting of all, because it requires no new mass whatsoever. On the first 3 roads, the star collapsed because something added weight to it. Gas from a companion, the body of another star, debris from the supernova. The bar got heavier. But on the 4th road, the bar does not get heavier at all. Instead, the support gets taken away. This is the road of spin down, and to walk it, we return to the supermassive neutron star. That object held above the cold line by the centrifugal scaffolding of its own rotation. Remember the supermassive star's predicament. Its mass is already too great for degeneracy pressure and the strong force to hold on their own. If it were sitting still, it would already have collapsed. The only thing keeping it alive is that it is spinning fast enough for rotation to prop it up. As long as it keeps spinning at that tremendous rate, it holds. But we noted, almost in passing, that neutron stars do not spin fast forever. They slow down. And now it is time to take that fact and feel its full weight. Because for a supermassive neutron star, the gradual loss of spin is not a minor detail. It is a death sentence on a timer. Why do neutron stars slow down? The main reason is their magnetic fields, which are staggeringly powerful, among the strongest in the entire universe. As the neutron star spins, this immense magnetic field sweeps through the surrounding space, and dragging that field around acts like a brake, bleeding rotational energy away, carrying it off in beams of radiation and streams of particles. The star is, in effect, slowly breaking itself, converting its spin into energy it radiates into the cosmos. The process is gentle, almost imperceptible from one moment to the next, but it is utterly relentless. The star spins a tiny bit slower today than it did yesterday, a tiny bit slower this year than last, and there is nothing that can stop it. The brakes are always on. But here's the detail that explains why the spin down road can take seconds in one case and an age in another. And it comes down not to whether the field breaks the star, but to how strongly it does so. The braking is caused by the field, so the stronger the field, the harder the brakes bite, and the faster the star sheds its spin. A neutron star with a colossal magnetic field brakes ferociously. It can wind down from a furious rotation to a sluggish crawl in a remarkably short time, which means a supermassive star with a strong field is living on a short fuse indeed, perhaps collapsing within seconds or minutes of its formation. But a neutron star with a comparatively weak magnetic field brakes only gently. The field drags through space but feebly, bleeding away the spin so slowly that the star can hold its rotation for an extraordinarily long time. A supermassive star like this, spinning fast and braking softly, can cling to existence for a very long while. Its collapse postponed far into the future, the support fading so gradually that the cliff's edge approaches at a glacial pace. So the very same road, the quiet loss of spin, can be a sprint or a marathon, depending entirely on how powerfully the star is magnetized. Two supermassive neutron stars of identical mass, born in the same instant, could meet wildly different ends, one collapsing almost at once and the other surviving long after, simply because one carried a stronger magnet than the other. The strength of an invisible field, threaded through the star, sets the length of its borrowed life. For an ordinary neutron star, this slow braking is harmless. It is below the line. It does not need its spin to survive. It can wind down to a lazy, sluggish rotation over millions of years and remain perfectly stable the entire time. But for a supermassive neutron star, the spin is everything. The spin is the only thing holding it above the line. And so, As the relentless braking does its work, the centrifugal scaffolding slowly, inexorably weakens. The extra support that rotation was providing fades a little more each year, and the star's effective limit creeps downward toward its actual mass. The two are on a collision course, and one day, after seconds or minutes or possibly very much longer, depending on how fast it was spinning to begin with and how quickly it breaks, the spin finally falls below the critical threshold. The rotation can no longer hold the mass aloft, and with no new weight added, with nothing having touched it from outside, the star simply crosses the line and collapses. There is something profoundly unsettling about this fourth road. The star is not destroyed by a violent collision or a rain of debris or the theft of a companion's gas. It is destroyed by the quiet passage of time and the gentle, unstoppable loss of its own spin. It is like a spinning top that stays upright only while it spins, wobbling more and more as it slows, until at last it topples. The supermassive neutron star is a top that, when it finally topples, does not just fall over, but vanishes entirely behind a horizon of its own making. And the timescale of this road is the most variable of all. A merger remnant collapses in milliseconds. A fallback collapse comes within hours. An accreting star takes millions of years to reach the edge. But a spinning down supermassive star, depending on its exact properties, it might collapse seconds after it forms, or it might survive for minutes, or it might hold on for far, far longer. A slow fuse burning quietly through time, its collapse delayed until the day its spin finally runs out. So we have our four roads, and it is worth holding them all in mind together, because each one tells us something different about how a stable thing becomes a doomed thing. There is accretion, the patient theft of a companion's gas over millions of years, ending in a sudden collapse the moment one last gram tips the scale. There is the merger, the violent collision of two neutron stars producing an overweight remnant that survives only milliseconds or seconds before falling. There is fallback, the rain of debris from the star's own birth explosion, burying it past the limit in the chaotic hours after a supernova. And there is spin down, the quiet, relentless loss of rotational support, in which a supermassive star is undone not by anything added but by the slow erosion of the very spin that kept it alive. Notice what these roads have in common and where they differ, because the pattern reveals something deep. In 3 of the 4 roads, accretion, merger, and fallback, the star crosses the line because mass is added. The bar gets heavier, but in the 4th road, spin down, the star crosses the line because support is subtracted. The bar stays the same weight, but the thing holding it up gives way. This is the full picture of how a neutron star meets its end. It is overwhelmed either because gravity is given more to pull on, or because the forces resisting gravity are weakened until they can no longer cope. Either way, the outcome is the same. The competition we have been tracking from the very beginning, gravity against the defenders, finally resolves in gravity's favor. And this is also where we can finally make sense of the strange, wildly varying timescales of survival that we noted earlier. Why does one doomed neutron star collapse in 1,000th of a second, while another survives for minutes or longer? The answer lies in which road it is on, and what kind of support is holding it up in its final phase. A hypermassive merger remnant is propped up by the most fragile supports imaginable. Searing heat and differential rotation, both of which vanish almost instantly, which is why it collapses in milliseconds. A supermassive star once its differential rotation has smoothed out, is held up by ordinary uniform spin, a more durable support that bleeds away gradually, which is why it can last seconds, minutes, or much longer as it slowly spins down. The length of the reprieve is set by the durability of the support. The more fragile the thing holding the line, the sooner the line is crossed. It is also worth lingering on a point I made earlier, but that becomes even clearer now that we have walked all 4 roads. Every one of these roads requires something to happen to the neutron star, a companion to steal from, another neutron star to collide with, a supernova that produces fallback, or the specific condition of being supermassive, of carrying more mass than the cold limit allows, which is itself the result of one of the mass-adding processes, or of being born that way from an unusually massive collapse. None of these roads describes an ordinary, isolated neutron star quietly minding its own business. And that matters enormously, because it means that the collapse into a black hole is not the default fate of a neutron star. It is not something every neutron star is creeping toward. The galaxy is full of ordinary neutron stars that will never collapse, that will sit stable and undisturbed for the rest of cosmic time, simply because nothing ever loads that final weight onto them and nothing ever strips away their support. Collapse is not destiny. Collapse is what happens to the unlucky ones, the ones caught up in these particular circumstances, the ones that find themselves on one of these 4 roads. The rest endure. We should also be careful to keep one more distinction crisp, because it ties back to the warning I gave about the original supernova. These 4 roads are about the transition from an already existing neutron star into a black hole. They are not about the original explosion that made the neutron star in the first place. A massive star dying in a supernova and leaving behind a neutron star is one event. That neutron star, later, traveling one of these 4 roads and collapsing into a black hole, is a separate event. Sometimes separated from the first by millions of years, sometimes by mere hours in the case of fallback, but always conceptually distinct. The supernova is the birth. These roads lead to a second death, a different death, the death of the neutron star itself. So we now understand with real precision how a neutron star arrives at the cliff's edge. We have traced the patient theft of accretion, the sudden violence of the merger, the returning rain of fallback, and the quiet erosion of spin down. We have seen that mass can be added or support can be subtracted, and that either one leads to the same destination. We have seen why the survival times range from milliseconds to ages, set by the fragility of whatever support is holding the line in those final moments. And we have seen, importantly, that this fate is not universal, that an ordinary undisturbed neutron star is not doomed at all. But in every one of these stories, we have stopped at the same place, at the edge, at the moment the defenders finally lose. We have said again and again that the star crosses the line and collapses, that it falls behind a horizon of its own making, that it becomes a black hole. And every single time, we have stopped right there at the threshold and refused to look over the edge. We have described the loading of the bar, but not the instant it comes crashing down. We have brought the star to the very brink of collapse 4 different ways, and 4 different times we have looked away at the crucial moment. It is time, at last, to stop looking away. The defenders have lost. Gravity has won. The standoff that has held for so long is about to break, and what happens next unfolds faster than light could cross the doomed star, in a sequence of events at the absolute limit of what physics can describe. The matter falls, a horizon forms, something escapes into the cosmos, or sometimes, strangely, almost nothing does, and what is left behind bears almost no memory of the extraordinary object it used to be. That final collapse, those last milliseconds and everything they produce, is where we turn now. We have brought our doomed star to the very edge 4 separate times, and 4 separate times we have looked away at the last instant. Now, we're going to do the thing we have refused to do all along. We are going to watch it fall. So picture the standoff one final time, that exquisite balance we have tracked from the very beginning. Gravity pulling inward, relentless and patient. The defenders pushing outward, the quantum stubbornness of the neutrons and the iron resistance of the strong force, with perhaps the borrowed help of spin and heat. For all of the star's life, these two sides have been perfectly matched, locked in a tension so fine it could hold for ages. And then, by whichever road brought us here, the balance tips. One last gram of stolen gas, the fading of a remnant's differential spin, the slow erosion of rotation. Whatever the cause, the defenders, for the first time, can no longer match what gravity demands. And in that instant, after all that time, the standoff doesn't just lean toward gravity, it shatters. Here is the thing that makes this moment so violent, so unlike anything in ordinary experience. The collapse is not a process that, once started, can be slowed or stopped. It is a runaway. Think about what happens the moment the outward pressure fails to hold. The matter begins to fall inward, but as it falls inward, the star gets smaller and denser, and as it gets denser, gravity at the surface gets even stronger. Because gravity grows more intense the more concentrated the mass becomes. So, the falling matter makes gravity stronger, and stronger gravity makes the matter fall faster and faster. Falling matter makes the star denser still, which makes gravity stronger yet again. It is a vicious circle with no exit, each step feeding the next, the collapse accelerating itself, gravity feeding on its own success. There is no new equilibrium waiting further down, no denser configuration where the defenders can dig in and make a new stand. Once the line is truly crossed, every possible state of resistance has already been defeated. The matter has nowhere to stop, and it falls fast, almost incomprehensibly fast. We are talking about a city-sized object, 20 kilometers across, and the collapse of its core unfolds in a span of time best measured in milliseconds, thousandths of a second. To get a feel for the speed, consider this. The matter near the surface, plunging inward, reaches speeds that are a substantial fraction of the speed of light before it has fallen very far at all. The entire catastrophic event, the transition from a struggling neutron star to something else entirely, happens faster than light itself could travel across the original star. Light, the fastest thing in the universe, moving at 300,000 kilometers every second, would take a tiny fraction of a thousandth of a second to cross a 20-kilometer object. And the collapse is over in a comparable flash. There is no slow crumpling, no gradual sinking. There is the standoff, holding as it has always held, and then, in a blink far too fast for any eye to register, there is collapse. Now, as the matter rushes inward and the star shrinks and gravity intensifies, something new enters the story. Something that has been waiting in the wings of every black hole tale ever told. An event horizon begins to form. To understand what this is, we have to think about escape, and about the strange relationship between gravity and the speed of light. When you throw a ball upward, It slows, stops, and falls back. Because Earth's gravity is pulling it down. To escape Earth entirely and never fall back, you would have to throw it upward at a particular speed, the escape velocity, around 11 kilometers per second for Earth. The stronger an object's gravity, the higher its escape velocity, the faster you have to move to break free. On a neutron star, the escape velocity is already a sizable fraction of the speed of light, which tells you just how ferocious its gravity is. But as the star collapses and the matter packs into an ever smaller space, the gravity at the surface climbs higher and higher, and so the escape velocity climbs too. Faster and faster you would need to move to escape. And then it reaches a threshold that changes everything. The escape velocity reaches the speed of light itself. Think about what that means. To escape from this region, you would need to move faster than light. And nothing can move faster than light. Nothing. Not matter, not energy, not even light itself. So at the moment the escape velocity reaches the speed of light, a boundary appears around the collapsing matter, a sphere from within which nothing can ever escape. Because escaping would require breaking the universe's most fundamental speed limit. That boundary is the event horizon. It is the point of no return. Cross it from the outside, falling inward, and you can never come back. And anything inside it, including light, is trapped, doomed to fall further in, because the only way out would be to outrun light, which is forbidden. I want to be extremely careful here, because the event horizon is one of the most misunderstood ideas in all of science, and the misunderstanding matters. The event horizon is not a surface. It is not a wall. It is not a solid shell, not a membrane, not a physical barrier of any kind. There is nothing there to touch. If you were falling inward and you crossed the event horizon, you would feel nothing at the moment of crossing. No bump, no resistance, no sense of having passed through anything at all. The strangeness is that the crossing matters only in hindsight. Nothing marks the moment as it happens. You would notice the horizon only later when you tried to turn back and found that every direction you could possibly travel led further in, with no path remaining to the stars behind you. The event horizon is not made of stuff. It is a location, a boundary defined purely by a property of space, the place where the escape velocity equals the speed of light. It is more like a line on a map than a fence on the ground. It marks a region with a particular rule, the rule that nothing inside can ever get out, but it is not a thing in itself. It is information about geography, not an object sitting in space. The collapsing matter does not slam into the horizon and stop. The horizon is not waiting there to catch anything. It is simply the invisible line beyond which escape becomes impossible, and the matter sweeps right past it, inward and inward, with nothing there to interrupt the fall. So now we can picture the formation of the black hole with real clarity. The neutron star's defenses fail. The matter begins its runaway plunge inward. As it grows denser and gravity intensifies, the event horizon appears. First perhaps deep inside the collapsing core where the density is highest, and then expanding outward as more and more matter falls past the threshold where escape becomes impossible. The horizon swells like a dark bubble growing within the dying star, swallowing the infalling matter until the entire collapsing object is enclosed within it. And at that point, from the outside, the neutron star is gone. Where there was a glowing, struggling, city-sized object, there is now a region of space wrapped in an event horizon, a black hole hiding everything that was once inside it behind a boundary that nothing can cross to come back out. And this raises a question that genuinely troubles people the first time they confront it. What happened to the surface? The neutron star had a real physical surface, remember? A solid crust, a crystalline lattice of crushed nuclei, billions of times stronger than steel, a genuine surface you could in principle have stood upon. Where did it go? The answer is that the surface fell inward along with everything else, plunging past the forming event horizon, and once it crossed that boundary, it was lost from view forever. The crust did not get left behind as a shell. It did not remain as some hard outer layer around the new black hole. It collapsed inward with the rest of the matter, swept across the point of no return, and vanished. After the black hole forms, there is no surface anywhere outside the horizon to stand on or to see. The solid, real, touchable surface of the neutron star is simply gone, fallen into the dark, beyond any possibility of observation. The black hole has no surface in the way the neutron star did. It has only the event horizon, that immaterial boundary, and behind it, hidden from us completely, whatever became of all that infalling matter. And here I must be honest about the limits of what anyone can say. What happens to the matter after it crosses the horizon, deep inside, is genuinely beyond our ability to describe with confidence. Our theories of gravity predict that the matter continues to fall inward, with nothing to stop it, toward a central region of unimaginable density. But what truly happens there, at the very center, is something our current physics cannot describe properly, because the conditions become so extreme that our equations break down and stop giving sensible answers. This is one of the great unsolved frontiers, the place where our best theory of gravity and our best theory of the very small refuse to agree. So I will not pretend to tell you what lies at the heart of a black hole, because nobody honestly knows. What we can say with confidence is everything up to the horizon, the collapse, the formation of the boundary, the trapping of light. Beyond the horizon, we reach the edge of knowledge, and the wise thing is to stop and admit it. Rather than spin a confident story, the universe has not actually told us. Now let us step back from the matter falling in, and ask a different question. The question of what gets out. Because while the matter and the surface vanish behind the horizon, the collapse is not necessarily silent. It can send signals out into the cosmos, messengers carrying word of what just happened. And here we encounter one of the most important and most subtle points in this entire story. So let me state it plainly before we explore it. What escapes from a neutron star collapse depends enormously on the specific scenario. There is no single answer. Some collapses are spectacularly energetic, lighting up the cosmos. Others may happen with startlingly little to show for them, almost quietly. The difference depends on which road brought the star to its end, on whether there was surrounding material, on the masses, and the spin involved. So as we go through the possible signals, hold on to this. Each one happens in some scenarios and not in others. There is no checklist that every collapse ticks. Consider first gravitational waves, those ripples in the fabric of space itself. Anytime mass moves in a violent, asymmetric, rapidly changing way, it stirs the space-time around it and sends out these ripples, traveling outward at the speed of light. A neutron star collapse, especially a violent one, can be a powerful source of gravitational waves because it involves an enormous mass moving and reshaping itself catastrophically in a tiny fraction of a second. This is particularly true for the merger road, where two neutron stars spiral together and collide. The inspiral, the collision, and the collapse of the remnant can all produce gravitational waves. A rising shriek of space-time distortion that we have actually detected here on Earth with extraordinarily sensitive instruments. The collapse from a hypermassive remnant into a black hole can imprint a particular signature on that gravitational wave signal, and reading those signatures is one of the few ways we can probe what is happening in these final moments. But notice the catch even here. A perfectly smooth, symmetric collapse, one where the matter falls inward in a perfectly spherical way, produces almost no gravitational waves at all, because it is the asymmetry, the lopsidedness, that stirs space-time. So even gravitational waves are not guaranteed. They depend on the violence and the asymmetry of the particular event. Then there are neutrinos, those ghostly, nearly massless particles that barely interact with anything. We met them earlier, born when electrons were crushed into protons during the original formation of the neutron star. A collapse can produce a burst of neutrinos as well, especially in scenarios involving extremely hot, dense matter being compressed even further. These neutrinos stream outward, passing through ordinary matter almost as if it were not there, carrying away energy and information about the conditions deep inside. In principle, a flash of neutrinos could be one of the messengers of a collapse, but neutrinos are fiendishly difficult to detect precisely because they interact so weakly, and whether a particular collapse produces a strong neutrino signal, again, depends on the details, on the temperatures and densities involved in that specific event. What about light? The kind of dramatic, visible fireworks we associate with cosmic catastrophes. Here is where the variation becomes most striking and most important to get right. In some scenarios, a collapse can produce intensely energetic electromagnetic signals, including a gamma-ray burst, one of the most violent and luminous events in the entire universe, a beam of high-energy radiation so bright it can be seen across enormous cosmic distances. This is thought to happen particularly in certain merger scenarios where the collapse of the remnant, surrounded by leftover material from the collision, can launch powerful jets and blasts of radiation. When two neutron stars merge and collapse, the event can be accompanied by a brilliant flash and a longer-lasting glow as the debris radiates, an event astronomers can actually observe. But, and this is crucial, this kind of fireworks requires material to work with. The gamma-ray burst and the accompanying light come largely from material around the collapsing object, from an accretion disk and surrounding debris being heated and flung about and channeled into jets. And there is something more that happens at this energetic end of the spectrum, something that turns the catastrophe into one of the great forges of the universe. When two neutron stars collide and a portion of their matter is flung outward rather than swallowed, the ejected material is unbelievably rich in neutrons, a spray of the densest stuff in the cosmos suddenly liberated into space. And in those conditions, an extraordinary kind of cooking takes place. The free neutrons are captured, rapidly and in great numbers, by atomic nuclei in the debris, building them up into heavier and heavier elements in a furious burst of creation. This is one of the few places in the entire universe where the heaviest elements can be forged. The gold in a wedding ring, the platinum in a piece of jewelry, a great many of the heaviest elements in existence are thought to be born in precisely these collisions, hammered together in the violent aftermath of neutron stars merging and collapsing. As these freshly made heavy elements form, many of them are radioactive, and as they decay, they release a glow, a distinctive shine that builds over hours and days, and then slowly fades. Astronomers call this glow a kilonova, and it is the visible signature of heavy element creation in the debris of a merger. In 2017, astronomers caught exactly this, observing the gravitational waves from two neutron stars spiraling together and then seeing the kilonova glow that followed, confirming that these collisions really do forge the heaviest elements. So a collapse on this road does not only destroy, it also creates scattering precious new material into space, where it may one day find its way into planets and rings, and perhaps into the bodies of living things. A catastrophe at one end becomes a forge at the other, and that points us towards the other end of the spectrum, the quiet collapse. Imagine a scenario with a very little surrounding material. Picture a supermassive neutron star, isolated, slowly spinning down over time, finally crossing the line on the spin-down road we described. There is no companion feeding it a great disk of gas. There is no recent collision strewing debris everywhere. There is just the star, reaching its limit and collapsing. In a case like this, the collapse could happen with remarkably little visible fanfare. The matter falls inward, the horizon forms, the star disappears, and there may be almost no bright flash to announce it because there is little surrounding material to heat up and radiate. The collapse could be, in a sense, almost dark. One moment, a neutron star is there, perhaps visible as a pulsing source of radiation, and the next, it is simply gone, winked out with no spectacular explosion to mark its passing. Some collapses may be among the quietest catastrophes in the universe, enormous in their physics but nearly silent in what they broadcast to the cosmos. And yet, even the quietest collapse might not be entirely silent, because of one final fascinating possibility tied to the spin-down road. Recall the supermassive neutron star, spinning fast, carrying its immense magnetic field, surviving only as long as its rotation holds. When it finally crosses the line and collapses, the matter that anchored that colossal magnetic field plunges across the horizon, and the field, suddenly cut loose, snaps and releases in a single abrupt instant. Some scientists have proposed that this sudden release could produce a brief, sharp flash of radio waves, a burst lasting only 1,000th of a second or so, an electromagnetic crack as the magnetic field is severed from the collapsing star. This idea has a vivid nickname, the Blitzar, and it has been suggested as a possible explanation for some of the mysterious fast radio bursts that telescopes detect. Those fleeting blips of radio energy arriving from across the cosmos, whose origins are still hotly debated. We cannot say for certain that any particular fast radio burst comes from a collapsing supramassive star, because there are competing explanations and the puzzle is far from settled. But the possibility is tantalizing. It means that even an otherwise dark and quiet collapse, with no great fireworks and no surrounding debris, might still send out one last whisper as it vanishes, a momentary radio chirp marking the death of a neutron star and the birth of a black hole. So why this enormous difference between the energetic collapses and the quiet ones? It comes down to whether there is material around the collapsing star and how that material is arranged. A collapse surrounded by a thick disk of gas with strong magnetic fields to channel jets can produce dazzling fireworks because there is fuel for the show. A collapse of an isolated bare neutron star with nothing much around it has no fuel for fireworks, and so it happens quietly. This is why we cannot say simply and universally what a neutron star collapse looks like. It might be one of the brightest events in the universe, or it might be one of the most subdued, and which one it is depends entirely on the specific circumstances of that particular star. This brings us to a question that should be nagging at you. If some of these collapses are quiet, and if the matter and the surface vanish behind a horizon we cannot see past, what can an outside observer, someone like us with our telescopes and detectors, actually detect? And the honest answer is that much of what we know must be inferred indirectly rather than observed directly. We cannot, for instance, watch matter cross the event horizon. That is genuinely impossible, not just difficult. As matter falls toward the horizon, the extreme gravity does strange things to the light it emits, stretching it, dimming it, and from our distant vantage point, the infalling matter appears to slow and fade as it approaches the boundary, its light becoming ever fainter and more stretched, until it simply fades from view. We never actually see anything cross. The crossing happens, but the image of it never reaches us in any clean way. So no astronomer can ever literally watch the moment of a neutron star's matter plunging across the point of no return. That event is, by the very nature of the horizon, hidden from direct observation. There is also a subtler kind of detective work that the masses themselves make possible, and it has become one of the most intriguing puzzles in the field. We know that the heaviest neutron stars top out somewhere around 2.25 to 2.5 times the mass of the Sun, near the TOV limit. And we know that black holes formed from collapsing stars typically begin at around 5 times the mass of the Sun and climb from there. Between those two values lies a curious, sparsely populated stretch that astronomers call the mass gap, a range where, for a long time, we saw very few objects of either kind. So when our detectors catch an object whose mass falls right in that gap, somewhere between the heaviest plausible neutron star and the lightest familiar black hole, we are faced with a genuine riddle. Is it an unusually heavy neutron star, clinging to the very upper edge of what the standoff can support? Or is it an unusually light black hole, the product of exactly the kind of collapse we have been describing? Often we cannot tell from the mass alone. The object sits in the gap, ambiguous, and we must hunt for other clues. A kilonova glow that would betray neutron star matter, or its absence, which might point to a black hole. Each object found in that gap is a small mystery, and the collapse of a neutron star into a black hole is one of the most natural ways to produce something that lands right there, in the no man's land between the two families. What we can observe are the messengers, the signals that escape before or around the formation of the horizon. We can detect gravitational waves from violent, asymmetric collapses, especially mergers, and read their patterns for clues. We can hope to catch neutrino bursts from the hottest, densest events. We can see the gamma ray bursts and the glowing afterglows from collapses that involve surrounding material. And we can sometimes notice the absence of something, a pulsing neutron star that was there and is suddenly, permanently gone. From these external clues, these indirect messengers, we piece together the story of what happened, much as a detective reconstructs an event from the evidence it left behind, rather than from having witnessed it directly. The collapse itself, the matter falling, the horizon forming, the surface vanishing, all of that we infer from theory and from the signals that leak out, not from a clear direct view of the event. The most dramatic part of the whole process happens behind a curtain we cannot pull back. Now let us turn to something we have not yet addressed: the fate of the neutron star's magnetic field and its surrounding plasma. Remember that a neutron star possesses a magnetic field of staggering strength, among the most powerful in the universe, and that this field is anchored in the star's matter, threaded through it, tied to the very material that is now collapsing. The field does not exist independently in empty space. It is held in place by the currents and the matter of the star. So what happens to it when that matter falls inward across the horizon? The remarkable answer is that the magnetic field, in the form that was anchored to the collapsing matter, cannot be retained by the black hole. There is a principle in black hole physics, sometimes captured in the memorable phrase that black holes have no hair, meaning that a black hole is an astonishingly simple object that retains almost none of the complicated detail of whatever fell into it. The intricate, twisted, immensely strong magnetic field structure of the neutron star cannot persist as a permanent feature of the black hole. As the matter that anchored the field falls in, the field that was tied to it is largely shed, radiated away in a final burst of electromagnetic energy as the horizon forms, snapping and releasing like a tangle of stretched rubber bands suddenly let go. The surrounding plasma, the charged particles that swirled in the star's magnetic environment, is similarly disrupted, some of it perhaps falling in, some of it flung outward. The whole elaborate magnetic structure that defined the neutron star's surroundings undone in the moment of collapse. This shedding of the magnetic field may itself contribute to some of the energetic signals we discussed. A final electromagnetic flash as the field is released. And this points us toward the deepest truth about what remains when the dust settles, when the collapse is complete and the black hole sits quietly where the neutron star used to be. The neutron star was an object of extraordinary complexity. It had a surface, a crust, layers of different matter, a superfluid interior, a mysterious core of unknown composition, an immense and intricate magnetic field, perhaps a furious spin and searing heat. It was a rich, detailed, complicated thing, and almost all of that complexity is erased. The black hole that remains is described completely by just 3 numbers: its mass, its spin, and its electric charge. That is all. Everything else, all the intricate structure, all the detail of the matter, the layers, the crust, the composition of that enigmatic core, every bit of it is gone from the outside, sealed away behind the horizon, where it can never be observed. The black hole remembers only how much mass fell in, how fast the whole thing was rotating, and what net charge it carried. The mass of the new black hole reflects the mass of the matter that collapsed. Its spin reflects the rotation of the original system. The whirling neutron star, or the merged remnant, its charge, which in practice is usually nearly zero, because cosmic objects tend to be electrically neutral overall, reflects whatever net charge was present. 3 numbers. After all of that complexity, all of that extraordinary physics, just 3 numbers describe what is left. There is something both humbling and profound about this. The detailed internal structure of the neutron star, the very thing we spent so much time exploring, the equation of state, the unknown core, the strong force resistance, the quantum stubbornness of the neutrons, all of it becomes externally unobservable the instant the black hole forms. We can no longer probe it, no longer measure it, no longer hope to read the answer to the great mystery of what that core was made of, because it is now hidden forever behind the horizon. The black hole keeps the secret. Whatever the matter truly was in those final moments, neutrons or hyperons or free quarks or something stranger still, the collapse buries the answer where no observation can ever reach it. The new black hole stands as a kind of monument to a question we can no longer ask of it. A smooth, simple object hiding an annihilated complexity. But the black hole does not arrive at that smooth, simple final form in a single instant. In the moment just after it is born, it is not yet perfectly settled. The collapse was violent and lopsided, and the newborn black hole is, for the briefest time, distorted, slightly misshapen, quivering, and it cannot keep that shape, because a black hole, left to itself, must relax into a perfectly smooth, featureless form determined solely by its mass and spin. So it sheds its distortions the only way it can, by radiating them away as gravitational waves, ringing like a struck bell whose tone dies down to silence. Physicists actually call this the ring down, and the comparison is exact. Strike a bell and it rings, vibrating. The vibrations fade in, as the bell radiates the energy away as sound, until it settles into stillness. The newborn black hole rings in just the same way, except it radiates ripples in space-time rather than sound, the wobbles of its birth smoothing out over a tiny fraction of a second, until it becomes the flawless, quiet object it is destined to be. And remarkably, the precise tone of that ringing, the pattern of those final gravitational waves, carries information about the black hole's mass and spin, a last signal sent out at the very moment of its formation. So, the death of the neutron star and the settling of the black hole are not two separate events, but one continuous motion. The bell struck and then ringing itself into silence. And if we are listening with instruments sensitive enough, we can hear the final note. And so we arrive at the end of the transformation, and it is worth drawing the line clearly between what we genuinely know and what remains uncertain. Because this honesty is the heart of good science. What we know with real confidence is the broad shape of the story. We know that a neutron star is held up by a standoff between gravity and the combined resistance of degeneracy pressure and the strong nuclear force. We know there is a maximum mass, the TOV limit, beyond which collapse is unavoidable. We know that spin and heat can temporarily raise that limit. We know the runaway collapse, once started, cannot be halted, and that it forms an event horizon, a true point of no return, which is a boundary and not a surface. We know the matter and the crust fall inward past that horizon and vanish from view. And we know that what remains is a black hole described by mass, spin, and charge. What remains genuinely uncertain is also significant, and we should not paper over it. We do not know the exact value of the maximum mass, only a range, because we do not know the precise nature of the matter in the deepest core, the equation of state that governs how stiff or soft that matter is. We cannot say with confidence exactly what signals any particular collapse will produce, because that depends sensitively on the specific scenario, the surrounding material, the masses and spins involved. We cannot describe what happens to the matter at the very center, beyond the horizon, because our theories break down there, and we cannot directly observe the most dramatic moments, the matter crossing the horizon, because the nature of the horizon itself hides that crossing from us forever. These are not failures of the story. They are the honest boundaries of present knowledge, the places where the universe has not yet told us its full answer. Let me leave you then where we began, but with new eyes. Out there in the galaxy tonight, neutron stars are holding the line, more mass than the sun packed into spheres the size of a city. their internal forces straining against gravity in a standoff that has held for ages. Most of them are ordinary, stable, in no danger at all, destined to sit quietly for the rest of cosmic time. And it would be wrong to imagine that every one of them is creeping toward a black hole, because that is simply not their fate. But some, the unlucky ones caught up in accretion or merger or fallback or the slow loss of their own spin, are traveling toward an edge. And when one of them finally crosses that edge, the standoff we have followed from the very start resolves at last, in a few thousandths of a second, in a runaway plunge that forms a horizon and hides the star behind it forever. What was once a glowing, struggling, intricately structured object becomes a silent thing described by 3 numbers. Its surface gone, its magnetic field shed, its great secret sealed away. Sometimes it announces itself with the brightest fireworks in the cosmos, and sometimes it vanishes almost without a sound. Either way, a neutron star has ended, and a black hole has been born, and the universe carries on, holding its remaining secrets close, waiting for us to learn how to ask the next question.